这是你的哦。
对对对。
这边也是。
好紧张。
这方面。
恭喜你赶上。
Hi, Chih-Fan. I'm Tomo. Hi, thanks for inviting me.
Oh, okay. Thank you.
It's very well written thesis.
Okay, thank you.
Splendid. ごめんなさい、直接来た。なんかもう起きたばっかだから直接来た。明日が。ああ、いいですね。完全に時差ボケじゃないけど、いつも夜型でやばい。さらに早いです。そう。なんか飛行機の時ね、なんか頭がなんか騙されて、なんか朝方に変わっちゃう。それがあるといいですよ。多分大丈夫。なんか YouTube で中継されるんですか？マジでなんか出てるんですけど。あ、そうなんだ。これ生中継なんです。あ、でもこの前、先週ぐらいに別のやつで学生がこれちょっとターンオフしていいから、ちょっと記号できる。特にだから、知らなかったんですよ。学生もしてる。すごいな、若い。YouTube ですごい。完全に世界一。と、もう一度開始を書いてる。それはしなきゃいけない。だからいつだ。
I also wanted to ask you about with the light all those weird pixels on the console. Okay.
Okay, I need sign.
Okay. I'll look at that. See how they deal with that.
But did you check the?
Oh, thank you. Okay.
Because the kappa map is weird. How about the function?
You mean
I don't have a bench.
Yeah. Because during the modeling.
Oh, sorry. I have that. No, okay.
So in the 2-X, it takes discretion angles and you're able to check the kappa cameras.
Okay, I'll have to look at that.
If you see the
yeah, I don't think I'm not going to come.
Okay.
Now.
That's which panel is that again?
third and fourth. First and second are excellent.
I don't remember seeing anything funny with that.
Is it written here?
So if the deflection angle has nothing to do with
Is this?
Yeah.
One of these are common.
Okay.
This is a common.
Because the kappa is not.
Yeah.
All right. Are you going to turn on the YouTube broadcasting?
Sorry?
Yeah, it seems like by default this is gonna be broadcasted onto YouTube.
Oh, really?
But last time I saw the student actually seems to have the right to the to,
Okay.
yes, I don't know.
I didn't know they broadcasted.
Broadcasted on the page A feed or the.
Actually, I don't know. Thomas.
Yeah, I connected and it was counting down on YouTube.
Yeah, and last time, last week for the students'
It's a
defense.
new thing, right?
Where
Yeah.
is-
The previous defense I went to, there was no live
Yeah.
broadcast.
Last week, the students say please turn off. So I think the student has a right to either.
So is that what the C is for?
Yes, yes.
Oh, very nice, very nice.
This is the live.
Yeah. My friend asked me to provide live
Oh,
video communication. See this.
okay.
You can take this.
He's coming in a minute. He'll be here. Is there some like paperwork or no? Oh, I guess it's on the thesis.
Another page.
It's like a grade, right?
Yeah.
It's okay. While we talk, you can print later. At some
Okay.
point, there's a closed session where we discuss it.
Okay.
You can print it that time. You close the door.
We need we need a external chair. A chair from maybe
I'm Tomo
from
from NT.
I see from Tsinghua.
Right.
So maybe you'll be the chair. Well, chair doesn't do anything extraordinary. It just you just have to monitor the talk.
Okay. I'll try my best.
Okay. All right.
So I cannot sleep.
That's right.
You cannot sleep. Right.
Me? Okay. So
Well, you
okay.
can sit there.
Let's start Chih-Fan's thesis defense talk. Did he talk with for how long?
40 minutes to 1 hour.
40 minutes to 1 hour, followed by questions. I think there'll be questions. Okay. So let's welcome Chih-Fan.
This is my title is First Use of Adaptive Optics Imaging to Constrain Cosmology with Gravitational Lens Time Delay. My name is Chih-Fan. My advisor is Dr. Xu Yu and Dr. Zhu. Okay, this is my outline. First, I will talk about my motivation, and then I will introduce briefly the basic theory, how gravitational lens to constrain the cosmology. And then I will talk about the advantage of why I want to use the adaptive optics system, and the challenge and the strategy for using the AO imaging. Then I will show the blind test with the mock data, and also the results from the cake AO imaging. And in the end, I will provide some. Okay. So there's several key questions on modern cosmology now. So what is the nature of dark energy? So what is the neutrino species, the mass of neutrino? What is the curvature of the universe? So who in 2005 said that H0 is the single most useful complement to CMB for dark energy studies. And we also can see this in the Rest et al. In 2011. You can see that it's from if you just use the CMB observation, there is a strong degeneracy. This is the total neutrino mass, and this is a number of the neutrino species. So you can see that there is strong degeneracy with the Hubble constant. So if we can provide additional information on the Hubble constant, so we can correct the degeneracy. So this is a famous Hubble key HSTT project, and this is another project for measure the Hubble constant. So in this is the degeneracy between the Hubble constant and the curvature. So in the Good et al. In 2010, it shows that the dot, the black dot, it shows that if we allow the omega, omega is -1, and we allow the curvature of the universe can vary. You can see that the strong degeneracy between the Hubble constant and the curvature of the universe. So if we have additional information on the Hubble constant, we can correct the degeneracy. So this is if we allow the omega can vary and also the curvature can vary, then we can see that without our current model, then we almost cannot provide any constraint on the Hubble constant. You can see the possibility of from 50 to 90 is almost the same. So it is very important to independently measure the Hubble constant. So in summary, the Hubble constant not only have the information to age the size of the universe, but also provide the critical independent constraint on nature of dark energy, neutrino physics, and spatial curvature of the universe. Okay, so this figure shows the measurement of the Hubble constant in the last decades. So there is three colors in this plot: the red, purple, and blue. The purple is used as standard candle to measure the Hubble constant. Then the blue is used as geometry. Then the red is the Planck and WMF9 result. They use the CMB observation. So in 2003, Spergel said that CMB observation do not directly measure the local expansion rate of the universe. So why is that the Planck and WMF9 has so tight constraint on the Hubble constant? This is because they derive the Hubble constant based on spatially flat Lambda CDM model, which means they assume the curvature of the universe is equal to 0 and the omega is -1. So it means that the result from the Planck and WMF9 result is highly model dependent. So therefore, it is very important to just directly measure the H0. Any discrepancy between these results won't be the pointer to new physics. So we can see that in the 2013 series paper, used the IXA 1131 strong lensing system with high delay. They can directly measure the Hubble constant within the 5.7 uncertainty. So there's two things in here. First, strong lensing with time delay is a competitive tool compared with other methods. And you can see there is a shift compared with the Planck WMF9 result. So is this indicate the new physics? We cannot sure now because the uncertainty in this measurement is still too high. So the result from the Planck WMF and the strong lensing is only within around 2.5 sigma. So so in the next decades, 2012 Suyu's paper showed said that in the next decades we want to beat down the uncertainty of the Hubble constant within 1%. So how can we do that? Aubrey and Marshall in 2010 shows that the thousands of length crystals will be found in the future, current future survey. So it means that it's one single strong lensing system. We can have the constraint like this, or even tighter. And we will have thousands of constraints. So it is made the goal to beat down uncertainty 1% is possible. So let me briefly introduce how gravitational lensing with time delay to confirm the cosmology. So if we have a background source, then the light emitted from background source will bend it by the photon galaxy. So if the projected mass density is higher enough, then we will see the beautiful image. So another thing, if the intensity of the background source like AGN, the intensity will vary, then because the light will pass through the different trajectory, we will see the time delays. So with time delays and by using the modeling the image, the observed image, we can constrain the potential of the photon galaxy. Then we have this and the time delay, and we can constrain the dt. dt is defined as time delay distance. The time delay distance is proportional to 1 over h0. And this is composed by 3 different angular diameter distance and the redshift of the photon length. So I want to emphasize in here, the Hubble Space Telescope image is necessary for precise measurement of H0, which means that the Hubble Space Telescope can provide high angular resolution. So every pixel in this image can constrain the potential, the mass distribution of the photon galaxy. And also, the HST has a known Poincare function, so we can define, we can know exactly every the light from the different position very accurately. Okay, so however, the HST cannot last forever. This is the last servicing mission is in May 2009. So the HST will not last forever, and then the time of the HST is limited. Because you can see this from the 2014. The 12% accepted proposal are for cosmology. But we know that in the future we'll have the thousands length quasar will be observed. So we need to find another way. And then the resolution is limited by the aperture size in 2.4 meters. So the resolution cannot be higher if we just use the HST. So why don't we use the ground-based telescope to solve all the problems? So this is the alternative approach. This sharp is strong lensing high angular resolution program, which is for studying the dark matter structure. So you can see this here. This is a Keck telescope, and this is a laser guide star. So by using the laser guide star, we can correct the distortion from the atmosphere. Then we can have a sharper image. And besides, the diameter of the Keck telescope is 10 meters, so it's larger than the HST. So we will have, we can have the high angular resolution. Okay. Let me show you the comparison between HST and the AO image. This is 0.05 arcsecond per pixel, taken from 3 letter on the 13 paper. And this is 0.04 arcsecond per pixels. Taken with the Keck AO telescope. So we want to ask you a question. Can AO data produce a similar cosmological constraint of HST data for tabular systems? We will put this question, we will answer this question in the end of this talk. Okay. So what is the challenge of using AO imaging? So this is a slow motion simulation of typical upper adaptive optic image. You can see this. So this is Russell's et al. In 1989 paper. Actually, this axis is the field angle, and this is the intensity. So if we if theoretical diffraction pattern like this, one here. So if the wavefront is distorted by the atmosphere, you can see the uncorrected. It's without the AO uncorrected. You can see that a point source will split into a block. And if we apply the adaptive optic system, you can see the corrected will become more concentrated into the diffraction limit. But however, there is still has a wind around here. So the challenge is we do not know what is the Poisson function look like after AO correction. So let me show you an example. This is the Poisson function. It's taken the star observed from the Cape laser gas star adaptive optic system. So you can see there's a right and a lot of features here. So how can we model this? You cannot use the analytical Gaussian profile. Obviously not. So we provide the method to interactive PSF correction scheme for obtaining the time delay distance. So I just mentioned here that the time delay distance is proportional to rotational. So this is a whole strategy how we do this iteration scheme. It looks very complicated, but actually it's not. So there's only two colors in this field, red and green. So the red is outer loop. We denoted the outer loop. Outer loop is to compose the lights by the current PSF. So actually, we just want to decompose in the red outer loop.
But this scheme is not limited to determining the time delay distance. I mean, the important thing is to find out the point space function of AO.
Yeah. It also can, yes.
And then once you have this point space function, you can apply to other
subject. You need, because every strong lensing has different point space function. Because it's different angles. So,
right. Well, what I mean is that not only limited to study time delay distance.
Okay. Yes. Okay.
So is that so? That's an interesting question. Are you using the fact that this is a lensing system to find out the correct PSF?
Yes, this is due to the strong lensing level multiple images. We know that the multiple images come from the same source. So we know because the angle is small, very small, the arc spectrum. So the pointer function around here is almost the same. So this method to find out the pointer function is only valid in multiple image system.
So you cannot use this method for example, star clusters, gravitational. Can you use these two? No.
Well, if the star cluster, if you have several stars nearby, then basically it just relies on, then you can, because if the PSF doesn't vary on the few arc second scale, then you can get the local, if there are multiple stars in that.
If the region is small, then you can apply this method.
Basically, once you go beyond 10 arc seconds, the PSF changes at the two locations. But locally, you can get the local PSF if there are multiple point sources.
So you're saying you're not using the information from lensing. But like for example, so lensing is from the same thing, same background source, right? So the residual from the PSF is also from the same system. And if you have a positive gravitational potential information, then you can predict what the residual looks like. Are you using this information to correct that?
Yes. We use because strong lensing the arc system, the light will contaminate to each other, right? So because the optics and strong lensing to constrain the arc, the light from the arc, so we compose the light from the arc to the
then you cannot use exactly the same thing for star clusters.
If the star is only if there is no other light in there, it's only the star in here, then I can use this method. Yes. Because in this system, because the light is contaminated with star rays, lens light, so the arc light appears as the agent light. So it's more difficult in here to apply this method. So if you have a system that is just a point source around a few seconds, and without other things, we can use this production also.
So what my point is like, so you have the same background source, and I say if you know the gravitational potential, then you could predict what the background means to this arc by it.
Mm-hmm.
So if your PSF is wrong, and I say if you have this additional residual, you can use that information to correct for PSF. But that's not the case if it's not gravitational lens system, say this additional residual after subtracting PSF, that might be just some background fault. So I was wondering if you use this information or not. If the answer is no, then you can use this system for other occasions. But if you're using this
if you sure that in your system there's no other light contaminant, it's only star, then you use this. Yes. Because when we use this information, we don't use just like when I
So for the isolated system, there's no need to worry about this contamination population agent. For this case, based on the lensing hypothesis, you simultaneously model. Yes.
So this is the if you compose this into the by using the current PSF, you compose the lens light, arc light. The arc light is from the lens edge, which is the lens edge post. Then we have the central lens edge. So we can get the lens edge in here. So now we go to the update the model PSF, and this is the inner loop. The goal of the inner loop is update the model PSF. So with so this is something like your if we have a four star in here, then we can have a model so we can get the residual. So the residual not if there is nothing else like contaminant, apply this method. So we just assume that the residual is due to the long function absorb the function of the light into the So so this is the correction grid exercise. This is delta omega J. So it's here's the delta omega 1, 2, and 3 is a vector. So this is a correction grid, fine structure of the proposed function. So we will have a residual in here like this. So this different color in here is the position of the center of the PSF. Then we apply the matrix M, which will map this vector into this vector, I to the control vector. So the M is encoded with the position and intensity of lens edge. But in this, we don't use the information from the strong lens because in the strong lens we can predict the intensity, the different intensity. But we don't use the prediction from the strong lens because there is a different reason that we find that there is a strong lens anomaly that the intensity is not just predicted by the strong lens system. So in here, this is just it's just fitting the light intensity. So we can define the chi-square of it's a difference between the residual and the correction grid. And so actually the chi-square is a function of the delta omega J. So in order to prevent from absorbing the noise, we apply we put the constraint on the noise penalty here. And so we want to minimize the arc here. So this is the method. So when we minimize the arc, we can find one solution. Oh, the main assumption in this strategy is that ESF does not change.
Is that assumption okay?
So this is okay. So it's small, but it's few seconds, only 3 4 seconds. So it's still okay in this case. And actually, at first we don't know. I will try and find out that the assumption is still okay because we tested the
So I want to know, you say there's not change too much, and then how much is too much? Like is it 2% or 10% or 50%?
We assume that this is the same. Within this area, it's the same. So we want to ask that if we assume that the PSF is the same, because this will different from the true result. So because in this system, it's true that already 2013 has already done using HSV. So actually we have a reference to test this method work or not. So in the end, we will compare the result by this assumption that PSF will not vary. Compare the result with the HSV.
This assumption, I think, also depends on the distance from a guide star. Yeah, how far away is the guide star here? So the PSA variation with the single conjugate AO, if the variation is going to get bigger if you are far away from a guide star. So
the tip tilt corrects for that. The tip tilt star corrects for that.
Is this natural guide star?
This is laser guide star, but there's a tip tilt.
Okay.
Yeah, so I thought together then it's because then you can shoot the guide star.
Yeah, you can decide the position
close to the system.
Yes.
Okay. So how far away? So the PSF variation it's like function like look like this. So after a certain distance, it gets steeper. I mean, you can actually quantify how much the variation you expect because this is one part of it. Like people observe star clusters and see what kind of variation.
Because there are not many after the strong system, so they should use laser guide star closer to make sure the difference of the PSI will not change. But because it's I'm not sure how.
Maybe you can take a look at later. Okay. You can see if it's a 2% effect. And also, usually, so yeah, I think the same here, right? But depending on the direction of the picture star, usually the direction of the elongation depends on the angle to the guide star. So, yeah, so if the guide star is align direction, it is perfect because the elongation goes the same way, but if it's perpendicular to the alignment of the sources, then you have a different elongation in a different way. It might be a problem. You can take a look at it later. I can show you the references. Okay.
So this is a reason why correction rate. We apply the correction rate and we minimize this R squared. But the R, the R is previous method. Then we add this, because we know this is our file structure of the PSF, then we add it to the model PSF and we get the new PSF. Then this is, we can go back to here and do the same thing.
So the model PSF is some kind of adoption. So the PSF is additional model on this one.
At first, the PSF can be taken from the nearby star. If there is no nearby star, we can just take the length itself and do the correct. And finally,
So the free form PSF model.
yes.
So there is also like expected PSF state from the previous observation. It usually LPSF is usually due to sort of campaign using some independent payload, which in your case is my instruction. So in the end, maybe we can check the derived PSF is sort of consistent with what people measure.
So we were testing one. So this is a visualizer of independent control scale for the function. Then this is so you can see the file structure correct PSF.
So just sorry, model PSF is allows electricity. Right? Model PSF is can be very difficult.
Oh, you mean the first?
Yeah.
Or by this method, we don't assume that it's a pixelated. So
Okay, so it's just
it's just
and model AGM.
oh, you mean the first PSF or
Yeah.
or first PSF you can just take it from the one cut from the strong energy system itself. So it will contaminate from with the arc